If you recall, yesterday, we talked about yesterday, modulo this class. On Tuesday, we talked about triple integrals. We're upgrading from double integrals to triple integrals. Functionally, we're doing the same thing, just more of it. We want to integrate some function of 3 variables over some solid. It gets a little bit messy if we try to think about a 4-dimensional volume. So the way we like, or one good way to think about this is to think about your function as the density at the points x, y, and z, and w is some solid. So x, y, and z can all be some distance, like meters. So w is some volume in cubic meters. dv can be some little chunk of that volume in cubic meters. Our function can be the density in kilograms per cubic meter. And so what we're calculating is the mass of the solid W. From a math standpoint, none of that matters. We're just evaluating this expression, f of x, y, and z times dv at all these points W. So W is some solid in 3-dimensional space. So W is a solid. And it's just a bunch of points x, y, and z at which we are calculating the expression f of x, y, z times dv. We're doing the same thing that we always do with integrals. dv is some small piece of the solid W. So dv is some small piece, a small cube in the solid W. So the dv is some small cube in solid W. It doesn't need to be a cube. I just don't want to write rectangular solid all the time. I'm just going to say cube. So dv is one of the building blocks in the solid W. And in that little small building block, we're assuming that f is constant, just like we always do. So we're evaluating the expression f of x, y, z times dv at all the points in W. The way we do this is we set up this triple integral, and we're still asking the same question that we did with a double integral. What's x between? What's y between? What's z between? We're still subject to the same rules that we set up for our double integrals. Early integrals can use functions of upcoming variables. Early integrals can use functions of upcoming variables. So for x, we can have functions of y and z. For y, we can use functions of z. But the last integral, the outer integral, only gets to use constants. So here's y using z, because z is upcoming. Here's x using y and z, because y and z are upcoming. But the outer integral only gets constants. When we set up these triple integrals, we're going to set them up in the same order that we set up our double integral. Since the outer integral only gets to use constants, we just start with that one, because it's easy to see the 2 planes that contain all the z values. Then we'll look at things in the yz plane and see where all the y values are. And then we'll look at the whole thing and see where all the x values, what the x values are between. So when we're setting up double and triple integrals, we start on the outer and then work in. When we evaluate, we start in and work out. Think about the thinking, think about what we're trying to describe, and think about how this is just an upgrade from double integrals. If we integrate the function 1, integrating the function 1 will just give us the volume of the solid W, because we're taking that little chunk dV, finding its volume, and multiplying it by 1. No units attached to it. Just like the integral over R of 1 dA will give us the area of region R. Just like the integral from A to B of 1 dx will give us the length of the interval from A to B. If we take this one dimension further and had a function of 4 variables over, I don't know what we'd use for here, H for some 4-dimensional chunk in R4 dot times D, I don't know, just draw a bigger V, like a super capital V for like 4-dimensional volume. We would be doing the same thing. We would get the 4-dimensional volume of, what do I call it, HH for hypervolume. These are the 3 that we go over because these are the 3 that we can picture. These 3 that make sense. Now, this is why we want, because we like to think in 3 dimensions, this is why I want to replace f of x, y, z, where the 1 here represented like a height, or f of x, y represented height, so we can have the volume of a 3-dimensional solid. Let's change our default thinking so we don't have to think in 4 dimensions. That f of x, y, z, we could think of that as the density at any given point. And what we're calculating here is the density multiplied by the volume to find the mass of the solid W. Any questions? Is everybody okay? All right. Let's take a look and write a triple integral for the volume of a sphere. X squared plus y squared plus z squared equals 1. The reason that we would want to do this is so that we can perform the calculation to see if it returns the thing that we expect it to return. We can calculate the volume of a sphere of radius 3, centered at the origin. It's going to be 4/3 times pi times 3 cubed, so 36 pi. So we already know what the volume should be if we integrate the function 1. So we'll know if our integral is communicating properly the things that we want to plug in. Let's think about what this will look like. My mental notes say, don't try to draw it, dude. What are you thinking? And every semester it's the same thing. Here we go. And it's like, oh no, oh no. Not bad, but I haven't started labeling things. Yeah. Yeah, that was strange. Looks like I'm still recording. Looks like we're all back. All right. Minor interruption, I guess. All right. So we need to set up, we want to set up a triple integral. One of the reasons that I picked sphere is that we can do things in whatever order we want. So let's go dx, dy, dz. So when we're setting up a triple integral, since the outer integral, in this case, the z integral, can only be between constants, we just need to figure out where the bottom and the top are. So down here at the bottom is where z is equal to -3, and up here at the top is where z is equal to 3. So that gives us our outer integral, z equals -3 to 3. What we want to think about is that we have the same kind of controls in our triple integrals that we had in double integrals that we had in our single integral. If, for example, I only wanted the top half of this sphere, instead of integrating from z equals -3 to 3, I could integrate from 0 to 3. If I wanted to come along and cut 1 unit off the top of the sphere and have this truncated sphere, I could just integrate from -3 up to 2. And then I'd give me the volume of a sphere with 1 unit truncated off the top. So we have a lot of control where we do this. The next up is our y's. And we'll have to come up with an x. So this is where I find out if I drew enough space. So the outer one is going to be the easiest to get because those have to be constant. Actually, the next easier one here is going to be the inner one. I want to know what x has to be between. So what are our values of x? And for that, we can just solve the equation, our initial equation for x. So x is plus or minus the square root of 9 minus y squared minus z squared. We expected functions of y and z. If we think about the values of x we're looking at here, the way I have my sphere oriented, this would be the front and the back parts of the sphere. The z is going to be like the bottom and the top of the sphere. So x, this is going to be like the front and the back of our sphere. The plus square root, that's going to be the front half of the sphere, the one coming out of the page, and the minus square root is the one behind the page. So we'll go from the negative to the positive. So we'll go from negative square root of 9 minus y squared minus z squared to plus the square root of 9 minus y squared minus z squared. The interval for the x using functions of the upcoming variables. So I was allowed to use functions of y and z. For the middle integral, also known as the Jan integral, we're going to look at what's going on in the YZ plane. X is taken care of. X, we're looking for all the Y's and Z's that we're going to be that are going to be involved in this X calculation. So let's look at what's going on in the YZ plane. Always draw the circle first. So down here is where Z is -3. Up here is where Z is equal to 3. If we look at this whole circle, this is just the circle y squared plus z squared equals 3. It's a circle of radius 3. So for ignoring the x value, this is y squared plus z squared is equal to 3 squared. Remember what the thinking is and how we set up what's y between. We look at it, for all the values of z between -3 and 3, for all the values of z between -3 and 3, for a generic value of z, what's y between? So for some generic value of z, what is y between? And we're going to go from the left side of the circle to the right side of the circle. So the y will be plus or minus the square root of 9 minus z squared. We're going to go from the negative square root on the left to plus square root on the right. This will represent the left and right sides of our sphere. So if I only wanted the right side of the sphere, I could integrate from 0 to the positive square root. If I only wanted the left side, well, I would just take the previous one that I did and say that's on the left now. But if I was starting with that one, I could integrate from negative square root up to 0 because of all the symmetry. Now, the question that had come up before, we have to remember when we can do this. If the density is uniform, then it's no problem. The left side and the right side are going to have the same mass. But if the density varies from side to side, if the density over here where y is -3 is 0, and the density over here where y is +3 is up to 100, then we can't just take the right side and keep it the same as the left side. We would have to integrate those separately. It does depend on y. Now, if it doesn't have to be uniform, but it would have to be symmetric about y equals 0, what we identify as being. But here we have all we're doing in our integral is integrating from the back to the front, from the left to the right, and from the bottom to the top. Any questions? If we integrate the function 1, this will give us the volume of the sphere, but we're not going to want to do that by hand because the first integral is going to be 2 times the square root of 9 minus y squared minus z squared dx. Oh, it's got y. Oh, sorry. 1 dx. But the first one's not the problem. Sorry. I'm getting ahead of myself. I know there's going to be a problem, so I just started talking about the problem. So our integral from -3 to 3, integral from negative square root of 9 minus z squared to plus square root of 9 minus z squared. And then the integral of negative square root 9 minus y squared minus z squared to plus square root 9 minus y squared minus z squared. 1 dx dy dz. The first integral is easy to integrate. The integral of 1 dx is just x. So our first integral is just an x evaluated from negative square root to positive square root. So that's the first integral. Now we just need to evaluate this at the positive square root minus the negative square root. So we're going to get 2 copies of the square roots. The x drops out because we're plugging in these functions of y and z. The problem is that this is sitting inside of a dy integral. The problem is now we have to integrate this with respect to y. And now we don't want to play anymore. Because this is where we'd have to use trigonometric substitution. And I know trigonometric substitution is your favorite substitution, but that's all we would have to do here. Incidentally, it's going to be a sine case. We're going to have to figure out what we want to use for the sine case. Remember the z squared? That's all just constant. We do have to figure out what a is equal to. There. It's going to be a sine case because I got stuff minus y squared and y is our variable. So y is equal to a sine of theta. But other than that, it's going to be a sine case. We knew it was going to be a sine case because when we integrate stuff, we expect some arc sine to show up. That's how pi gets entered into all this stuff. We know that our answer needs to be 36 pi. Pi's got to show up somehow when we're just plugging in -3 and 3. It must be because there's some arc sines running around. But the substitution we want to make is a something times the sine of theta. Yeah, y equals a sine theta. That would be the trigonometric substitution we want to do. If we're going to do a sine case, which we think we want to do because of the minus y squared. If it was plus y squared, that would be tangent case. If it was y squared minus, that would be tangent, secant case. Any questions? How's everybody okay? Can you tell which integral I'm not going to be doing today? This one. Yeah, that's why. Because we know that there are better coordinates for integrating round things, like spherical coordinates, where a sphere is just a rectangle. And we can describe it with interval. Any questions? How's everybody okay? Everybody looks so sad. I feel sad. They're still mad about yesterday. You got your trigonometry on my calculus. You got your calculus in my trigonometry. It's 2 great places to take great stuff. I don't know why anybody's complaining now. Y'all remember trigonometric substitution? That's why you're stressed out, because you're worried that there's going to be like a quiz right now on trigonometric substitution. Oh, that's gonna be a problem. Put your stuff away. We're gonna have a quiz right now on trigonometric. I'm just kidding. That's how you find out how committed you are to avoiding trigonometric substitution. You're like, oh no, I can't do the quiz right now. It's like, oh, why is that? I have a doctor's appointment for my broken finger. Your finger looks fine. And you're like, slam it on the desk. And like, oh, ow, I'm going to be at the doctor's. That's right. My phone rang. I gotta take this call. Can I use the restroom? Yes, of course you can do your taxes. This is America. You have to. That, by the way, is the most messed up test that there is. Because the IRS is like, all right, you got to pay us. How much? We're not telling you. You got to figure it out. It's like, motherfucker, this is a math test, isn't it? Like, yeah, and if you get it wrong, although if I like give you a test and you get it wrong, then it's like you lose some points, right? And then maybe I'll get a chance to make it up. But if you get the IRS test wrong, it's like, oh, you go to fucking jail, dude. Yeah. In like most other places, it's just like, oh, here's your bill. And you're like, oh, okay. But anyway. We have H&R Block. Will someone think of H&R Block and TurboTax? They'll go out of business if they didn't have a reason. Oh, shit. Oh, well. Any questions? Next week, what we want to do is learn better coordinates. So that's the other reason that we try to calculate the volume of the sphere and run headlong into trigonometric substitution that we don't want to do. Because we want to look at different sets of coordinates and the things that we'll have to do to make those sets of coordinates fit into the description. Remember what the description is. This dv factor right here represents a volume. It's the length dx times the length dy times the length dz. It represents a volume. It's a length times a length times a length. So when we start looking at polar coordinates and cylindrical coordinates and spherical coordinates, we start using angles as measurements. The problem is, if I have a d theta, that's some small change in an angle. It is not part of an area. It's just a change in angle. It doesn't give us a length. And that's what we want to think about next week. Any questions? Comment? Snide. All right, that's it for today. That's it for this week. I will see you all on Monday. Everybody have a good weekend. And thanks for playing.